Okay, so hello everyone. I'm Marek Niewiadomski. I work in Astorino in Cracow here.
Trochę bliżej mikrofonu.
Okay. I work here in Astorino in Cracow, and I'm a developer of this robot you can see here. So we'll talk about Astorino robot in a minute. Okay, so we declare that Astorino's revolution in education in the robotics field. So basically, we think that Astorino is a game changer in schools, universities that teach robotics, but in the matter of production and later work in the factories. So industrial style robotics, not university style robotics like implementing ROS or something like this, but more into the industry, more into the later on for students to work in the companies, in the factories. So why this robot is so different? So you can see we have made some research on the market how the system of teaching in robotics in Poland or general in many other countries also looks like. So most of the time on the university, on the school or tech school, there is one robot. In most cases this is the old one. If there is a new robot, then students cannot touch it because you can break it, it's dangerous, it's big. If something breaks, then the repair cost is very high, and so on. So a lot of theory, really touching something physical in the university. From my point of view, I finished University of Science and Technology here in Cracow about a few years ago, and and most of the classes from robotics lessons were you have a MATLAB, you get a lab view, and make some fancy charts, and you see the axis of this kind of robot is moving like this. Nothing more. You have the Heidelberg table, write some data, good. But also I had a Lego robot. So I had classes that was conducted with Lego Mindstorms, which was good. For my opinion, it's good for high school, not the university. And in the past, what can you choose? First of all, you have the low-cost robotics, as you showed before. So the low-cost, made of mostly of Lego or some cheap plastics or servo from models. It's safe. It does not teach solution used in industry later on, and it does not prepare students and pupils to work in companies later on. So it's very difficult also for us as Astor to find some guys or girls who know how real industrial robots are working. So this is completely different solution. And on the second hand, you have the normal industrial style robot with high cost. It requires additional safety systems like safety fans, lasers, and so on. It of course teaches solutions that are used in industry and prepares students to work in later on companies. So this is the main idea that's behind that really. So we need to combine these two words together. Therefore, the Astorino robot is something in between. It's not a toy, but it's also not industrial style robot totally. It can mimic all the functions of the industrial style robot, the programming language, the uses of PLC control, all the factory communication protocols, like for example Modbus TCP and so on, and yet the cost is really low comparing to the big robot, and it's safe as a toy robot. So basically this is a robot with 6 degrees of freedom. Robot design is based on the 3D printing technology. So the entire robot arm is 3D printed. It uses steel gearboxes for all metal parts, like gearboxes, stepper motors and so on, are from metal. It's programmed in simplified version as language. As language is the programming language of Kawasaki robots. So basically, if you know how to program the Astorino, you know how to program Kawasaki robots later on, or basically, you know mostly all of them, because all the programming languages for industrial robots are very similar. Yeah, and why it's 3D printed? It's 3D printed because during school hours, it's natural, then you can make some mistakes. And if you make some mistakes with the big industrial robot, it can harm someone, or you can damage the station or itself. This one, if you make a mistake and something breaks, you can reprint the part and make the robot work again in a matter of hours. Basically, the payload is about 500 grams, repairability 5 of a millimeter. Yeah, it's based on the stepper motors working closed loop control. It uses something like Arduino, so TNC 4.1 microcontroller as a main board. It has 3.3 IOs in standard and the SD card for user data. So basically, how does it work? So here you can see the normal industrial robot is executing the same program. So the Kawasaki robot is executing this program here, and the same program is loaded to Astorino and is executing the same. As I mentioned before, it's programmed in AS language. So you can see here a program running on this robot. So you can see that the programming language is very simple, very easy. It's something like BASIC. Yeah, we have some additional options also. So like 24 volts I/O module for industrial style applications. Belt tracking technology, so conveyor tracking with maximum of 2 additional encoders. Machine vision programming Python. Cube speeder, that is the one in the middle, aluminum based like grippers, linear track, and available services like, for example, Modbus TCP, serial communication, for example, MATLAB or LabVIEW, and collision detection impact sensing. So after all of this, you might think this is a big company product, but not. I did it. Yes, so how did it all started? It's all started in I think 2010. With discovery of 4-bot and microcontrollers. That was quite a discovery for me, because on the university there was nothing about this. So I came to this knowledge from internet and from my colleagues from the university. Then in 2011, first robotic project on the bachelor degree. 2013 a master's degree, and so on. So the first 2011 it was the hexapod, but to a degree it was based on the Atmega, the 8 this time. So a long time ago, with no Arduino project and nothing more. So you can see some PCBs that are made, homemade PCBs, and so on, to make it work. Later on.
One question: was that filmed on AGH?
Yes.
I recognize
B2 booming, yeah. Yeah, so later on, 2013, the second robot, and it changed entirely my mind, because I was thinking how to make this robot. I designed all of these PCBs, programmed all of these controllers, and so on, and it was very, very complicated. I discovered that I can order PCBs, not to make at home ones. And I made this robot, that robot, the first one, as a master degree. It was super complicated, too complicated, I think. Right now, I think it was too complicated. Later on, 2016, first 6-axis robot prototype, and then Delta robot version, second version, with the conveyor and the linear and the vision system that was looking for these cubes on the conveyor, and the robot was picking the cubes from the conveyor. And this time also it was super complex, also too complex. So remember, if you're making something, don't make anything too complex. It's always the point of failure at some point. Do as simple as possible. This is what I learned from all these years. So this was also the second. This was the years that I was looking for microcontroller that can make this work. So first of all, it was Arduino Duo, but it came out it was too slow. The second thing that was very discovering for me, I don't need to program everything from the beginning. So I have the Arduino, I can use the libraries. That was the second discovery I made during the years of developing this robot. So don't make everything from the beginning. Later on it was Intel Edison, but it turned out it was very, very powerful, but it had some other problems. And then later on I found these TNC controllers. I really recommend them. They are pretty good. And 2020, so we had the COVID era. I was locked in the apartment. My wife was pregnant. She was going to sleep at 7 p.m. and I had a lot of time in the evening to make some new robots. And this was this Astorino robot, the first prototype of this robot. So you can see you do not need some fancy laboratory, you don't need some fancy desk. It was the old desk from IKEA with some screws in the back, some 3D printers there from the back. So some very simple 3D printer like Ender 3 3D printed this robot. So you don't need really big budget to make something like this. All the gearboxes were bought from AliExpress. All the stepper motors, everything was purchased from there. So to make it cost effective, because I had to pay it for myself, yes, for my own budget. And during the process of developing this robot, I started to think how to make it as simple as possible, how to cut the cost as much as I possibly can. So Yeah, of course, there are some robots on the market. There are some robots even on the internet that are using, for example, brushless motors with some fancy system of control. But that was not the case in this one. I wanted to make it as simple as possible, as cheap as possible, as repairable as possible. Because if something, for example, the driver breaks, or the electronic brakes, you just need to unscrew 4 screws, replace the driver, and it's ready to go. But there are many robots on the internet, or even available on the market, that if something breaks, you need to deconstruct entire robot to make it work again. And how it's going? This is Kawasaki product now, because we as Astor are distributors of Kawasaki Robotics. Some CEOs came to Astor for a visit, seeing this robot, and wanted to use this. 2 of these robots went to Japan. They were evaluated by Kawasaki Robotics team in Japan. They told us it's okay, gave us some so-called Kaizen points to improve the design, improve the software, and then gave us the agreement to use the Kawasaki Robotics logo on the robot itself. So basically, this robot arm is capable of doing all the stuff that industrial style robots can do. And this is what we want to achieve, yes? So that change the way it's being learned. So to give the students not 1 robot in the laboratory, but 1 robot per desk. So 2 students can, for example, program the robot. You have 4 or 5 robots per classroom. It completely change the direction of how you learn how to program robots. Because programming robots is a little bit different than programming, for example, Windows application or Linux application, something like this. If you make a mistake, then it's going to do physical harm to itself, to the station or something else. You need to think of many things that you don't need to think during programming on the computer. And we want to teach young students how to program a robotic arm. Okay, so how it's going? We have delivered many, I think right now is about 25 units already delivered to some of the schools and universities. So we have one in University of Science and Technology, is this Silesia Polytechnic, and other schools in Poland in general. But also we have some projects running in France and also in Japan, UK, and also one is right now being sold, is already sold, and it's going to Egypt. Yeah, so thank you. This was a brief presentation. Yes, so if you have still time, you can try to run it.
There are some questions, I think.
Yeah, sure. So
Mine is just sharp, like the most like crucial question. What's the price?
the price is fixed. The price is worldwide set by Kawasaki Robotics, and it's 5,300 euro.
Okay.
So it's not hobbyist robot. So it basically need a lot of budget if you want to make this at your desk.
That brings more question why the HDH button.
They got a big discount.
Like you paint them.
I understand that this robotic arm is right now Kawasaki supported, I would say, yeah. But you have said that this simplified Kawasaki language. Does it mean that you are using standard programming IDE, or you are using some dedicated one for this robot?
Okay, so basically the ID is custom. It's made entirely for this robot arm, and only the programming language is the same as in Kawasaki. So the program itself looks similar to the one that is in Kawasaki robots, but it's different. But the programming language is the same. So basically you can write a program on this arm, take a pen drive, take this program to the Kawasaki robot, plug it in and run it the same. So the robot will behave the same.
And can you communicate with it only using C++, let's say?
No, it's closed. So you cannot use C++. It's programmed in C++. But you cannot use right now. Maybe in the future we will add some libraries or APIs to control the robot via this system, but right now it's closed.
Is there a possibility to calculate joint's position on the computer and stream it to the robot?
Basically, yes, you can do this, but I think you don't need to do this because entire calculations on the inverse and forward kinematic and so on are calculated in the controller that is here. Basically, the PC is used as a programming tool, I would say. So you need to use this software to move the robot and teach some points and write the program, but nothing more.
Okay. And there is a lot of LCD screens on these different motors. What is the purpose of the screens?
Basically, the screens are used only during the calibration, so you need to calibrate the encoder with the stepper motor, and this screen is just for going through menu. And later on, it's showing the position of the motor shaft, and that's all. Basically, you can just remove them after all, but many professors, in fact, and teachers told us leave the screens; they look awesome. So,
And probably it's helpful to teach about the movement of the arm itself.
yeah, probably you can also do this. Yeah.
How many different versions that you have, maybe in terms of joints or shape? How many different versions you have?
No, right now. Maybe.
Version.
Yeah, only this one. Maybe in the future we will add some other options also. Yeah. So basically, this is the software. Yeah, in the software this is embedded visualization tool. And basically you can use this robot as normal industrial style robots to move in all directions with interpolated motions and so on and so on. Yeah, you can store some points, move to these points with certain commands. Set them home position, teach the tool dimensions and that are being used in the calculation of inverse and forward kinematics. Use the wizard to calculate the tool automatically like in normal industrial style robots. And then points, you can restrict the motion area, so the robot, for example, will not hit the floor. Then you can program your robot here. And use some terminal to talk with the robot. Use Modbus, for example, use inputs and outputs, make some backup of the robot and so on. So all the stuff that is really necessary to know how to program and use industrial style robots are here.
Question.
Yeah.
Do you plan to add a teach pendant for the robot?
Yes, we are planning to add the teach pendant for this robot. Frankly, we now have the first unit made, and now the programming time for this teach pendant, because basically to use the teach pendant we need to rewrite this C# application into the C++ application into the microcontroller that is inside the teach pendant itself.
I have a question, another.
Yeah.
Is there any file system to store multiple programs on your robot?
To start multiple
To store and
Yes. Yes. You can store as many programs as you want. So for example, here we have a 10 program, but I can create a new one.
Okay.
Oh, so. And then I can upload this program to the robot, and it's stored in the SD card in the robot base. So basically, you can make as many programs as you want until the storage capacity is over. Then you can of course run the program. Oh, sorry. The belts got loosened because of the temperature in my car. Yeah, because we joined 5 and 6 are transmitted by the belts.
What have you used for the controller itself? Is it an Arduino board?
Yeah, it's something similar to Arduino. It's in fact TeamSeek 4.1. TeamSeek 4.1 is I think it's the most powerful microcontroller right now, compatible with Arduino libraries. So basically it's a 600 MHz 32-bit microcontroller that is really powerful. So basically, it can run all the kinematics, all the linear algorithms. It can run the Ethernet communication and serial communication at the same time. So basically, I think this is the most powerful microcontroller right now. Even the Raspberry Pi, I think this new one is not so powerful as this one. Yeah, the vision system. Yeah. So machine vision program in Python. Basically, you can use any kind of vision system you like. It's just a matter of sending some data to the robot via serial communication.
Okay, and it is mounted on the TCP?
Yeah, you can mount it whatever you like. You can mount it on the robot itself. You can mount it under some hole here, to make the static vision inspections and so on.
And we can connect it to the controller board.
Yes, basically yes. In fact, this vision system, maybe some of you heard of this. It's called OpenMV. It's open-based program in Python vision system that we implemented to work with this robot. So basically, it's you can use any kind of camera that is just sending data to the robot. So basically, the vision system in robotics works like this: that you make a photo and send coordinates in the robot map, in the robot base coordinates to the robot, and then go pick something or send information if your detail is okay or not.
So the program is executed on the computer that is connected to the robot, right? When we talk about the vision.
No, vision also no. Vision is also computed on this camera.
Okay.
So you program this via special software, connect it to the computer via USB cable, program this in Python, and then connect only the serial communication lines to the robot.
Can it move all of those degrees of freedom at once?
Yes. Yeah. So, where's the next? So let's stop the program. Yes, and for example, I can teach some points. Let's teach the points. Yeah, for example, this one will be P0. Then I can teach the second one. You can see the TCP. This point is moving a straight line in space. Change the orientation a little bit. Yeah, and start this second point. Then I can go to all these points again, like linear motion and any other motion. Or basically I can use okay. Set position here. Or basically I can use commands in the terminal. So we have the terminal here. For example, I can type some commands. Do home, for example, or do move P0, that means do linear motion to point P0. Yeah, and so on, so on. So basically I can use this in terminal, or I can use all of these commands here also in the program. And basically you can use also many other things, like for example for loops. You can use if statements and so on. So basically, you can write really complex application in this solution to make an application that will look like and behave like in the factory later on. So
I know it's not like a practice that you have said on the beginning, but do you have the full simulation mode in your software, or is always connected with the machine?
yeah, the robot itself must be connected because, as I mentioned before, the controller is on the robot base. The software is only using this for controlling the robot. But let me change the screen. But upload program. But you can activate this robot in this song called dry run mode, in which you can see I can execute the program. The robot is executing the program, but the robot itself is standing still.
So you are cutting off the robot arm, but you have to use your controller to compute the
Yes.
trajectories, yeah?
Yes,
So
yes.
And is ROS compatible in any kind of, I mean, not for ROS, ROS?
Not yet, but we are thinking about adding ROS to this robot.
I mean, if you want to like put it on a mobile robot and communicate with this, how should it look like? I mean, the communication part.
I think the communication part can be completed by the serial communication. You can send some frames, for example, and basically send and receive some information. You can use in this robot arm. You can use, of course, you can use variables. For example, I can define, for example, I variable and something more. I can use string variables. I can use, for the serial communication, I can use send command, and by send command, I can transmit the string variable. So you can, in many ways, communicate to external equipment. So you can send, receive string variables, then later on cut from the string variables some values, and then change these values from string to integer, or for example real variables, and then use them to create some points. So for example, I can create point. So basically it will look like something like this. So I can create a point from the variables I received from the serial communication, and create the point from these variables, and then make the robot go to this new point. So yeah, so basically, yes, you can do this, but you need to remember that this is not a so-called cobot. Yeah, so it has some features of the cobot system. Yeah, it has some impact sensing and so on, but it's not like universal robots or something like this. Okay, so thank you.